Okay. How do you represent numbers that have fractional parts in a word, in a system, in a digital computer, in a system, in a computer system, say? You assume a binary point position, okay? So you say, well, this is a 16-bit number, okay? This is a 16-bit number. You assume that anything you assume there is a binary point in this position, and anything to the right of that is the fractional part. Anything to the left of that is the integer part. Okay? This notation is called fixed point number representation. That means the number is fixed, is right over here. Okay, so any of the numbers we have seen before, I'm not going to go that far back, but for example, there was 19 point something, let's say 19.625, okay, to represent that in this fixed point, I say 625 is 1, 0, 1. But then I have 1, 2, 3, 4, 5, and therefore 2 zeros here. 19 is 1, 2, 4, 8. 16 is okay, is 1, 1, 0, 0, 1. Together 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15, 16, that's 16-bit fixed point with 5-bit fractional part representation for the number 19.625. Well, that's fine. That's an easy way of doing it. If you want to do fixed point fractional numbers only, you put the point over here, and then the rest of it will be your fractional part. So it's easy to do it, but then you are limited as to the size of the number that you are representing. Another representation is called floating point numbers. Floating point numbers, you have a mantissa, and then you have an exponent, and then you have a radix. A 16-point representation, a 16-bit representation would be like this. You take the mantissa part, and then you would say the mantissa part would be certain number of bits, and then the exponent will be 2 to n minus 1, okay, and all right, with this fixed point representation, we are not going to be able to fit a lot of numbers in 16 bits, okay? And also, we are not going to be able to represent numbers with a lot of precision. But then it's easy, right? In cases where you need more precision and you want more numbers to be able to fit into, let's say, more space, or some space, what you do is you go into the floating point representation. Floating point representation is really nothing new. You have already done floating point for decimal numbers, right? For example, you say 25 times 10 to minus 6. Okay, and so this becomes the exponent, and this becomes the mantissa. And we're going to be doing the same thing here. The example I'm using here, let's say that you have the number 5. Okay, number 5 can be represented as 5 times 10 to 0. Okay, so 5 is the mantissa. 10 is the base, but here we are not going to be doing base 10, we're going to be doing base 2. And then 0 is the exponent. I can do 0.5 times 10 to, okay, I'm sorry, I can do, instead of this, I can do 5 times 10 to minus 50 times 10 to minus 1, okay, which is the same thing. Now let's look at the binary way of doing this same thing. I have the number 5, which is 101, okay, times 2 to 0, okay. That means initially I have a 0 for the exponent and I have 5 for the mantissa. I could put 5 right over here. 1, 0, 1, 5 right over here. Okay, with exponent of 0. But then I'm not going to do this. I'm going to shift this to the left. Okay. And as I'm shifting it to the left, I'm adding 1 exponent. But the thing is, shifting this one place to the left, that becomes, this one goes here. Instead of 2 to 0, becomes 2 to 1. 2 to 2, 2 to 3, 2 to 4, 2 to 5, if 1 comes over here. But if I'm shifting it all the way to the left, okay, and if I always have a 1 on the left-hand side, why bother writing the 1? Okay? Why not say that I'm actually shifting this 6 places to the left, and I always assume there is a 1 all the way to the left. This way, I can fit more numbers into this space. And therefore, I shift my 5 all the way to the left, make it 0, 1. I assume there is a 1 on the left-hand side, which I never represent. And then this becomes this number over here, which is 1, 0, 1. This 1 is assumed. 0, 0, 0, 0, 0, 0 times 2 to minus 6. Okay? Times 2 to minus 6. Well, that's good. Now I have to represent the exponent. The exponent is always negative because I'm always shifting numbers to the left. It means that to compensate for shifting to the left, I have to have negative exponents, right? So the number is always a negative number. Since the number is always a negative number, there's no point in saving or in using a position for the sign bit of the number. Okay? Again, to save a bit, what I do is instead of representing minus 6 as a 2's complement or as a sign and magnitude number, since it's always negative, I represent it as what is called excess. Okay? I have 1, 2, 3, 4, 5, 6, 7, 8. Okay? 8 gives me 127 excess. Okay, this is missing. 127 excess 127. That means minus 6 in excess 127 becomes 127 minus 6, and that becomes 121. So instead of representing a 6 as 0, 1, 1, 0, 0, 0, 0, 0. Instead of representing it this way, okay, I subtract, well, that's a 6, okay? That's a 6. Instead of saying that I want to represent it as a 2's complement minus 6 or something, I say I represent it as excess 127. Excess 127 means that 121. Therefore, minus 6 becomes 121, and this number is 121. That's 1, 2, 4, 8, 16, 32, 64. That's 96. Okay? And that's 120 together with this and a 1. That's 121. 121 in excess 127 represents number 120. I'm sorry, number minus 6. And therefore, my number 5 becomes in 16-bit floating point representation, becomes 0, 1, 0, 0, 0, 0, 0, 0, continuing 0, 1, 1, 1, 1, 0, 0, 1. Okay, this 16-point representation has 8-bit mantissa, okay, and then 8-bit for the exponent. For more precise representation, we go up to, let's say, 32 bits, but then in addition to having the number itself, we also want to have possibility of adding a sign to it, and therefore a 32-bit floating point representation, which is a standard form of representing 32-bit numbers, becomes something like this. You have a 32-bit, the leftmost bit, bit number 31 is a sign bit. Your exponent is excess 127, that means minus 6 becomes plus 121, okay? And then you have 23-bit for the mantissa, and dropping a 1 to the left-hand side, assuming a 1 to the left-hand side of the mantissa, is always done. That's called normalized, and therefore you have a 23-bit normalized mantissa. For a better precision, you go up to 64 bits. Again, you have the sign bit all the way to the left. Then you have 11 bits for the exponent. 11 bits for the exponent becomes the negative numbers, or the negative exponents are represented as excess 1023, okay? Meaning that if you have minus 6, then it becomes 1023 minus 6 becomes 1017, okay? 1017 you represent in the exponent part, and then you have 52-bit normalized for the mantissa part. Okay, we are done with number representation, and we have covered basic number conversions. We have covered fixed point, we have covered floating point, and we have covered 2's complement, okay? And we have also talked about the concept of overflow, and next we will be getting into gates and building some logic. Maybe a logic that we would be building would be a overflow detector circuit. It would be a circuit that adds 2 numbers together, and we'll be seeing those in the next part. All right.